All right, so let's take a look at section 9.2. So yesterday we did 9.1. That was on parametric graphing. Still the same kind of axes. You still have an x, you still have a y, but the difference is you have a separate equation for each axis. One equation gives you x values of your coordinate, the other one gives you the y's. We're going to see a connection between polar and parametric. We'll get into all that more tomorrow. But for today, I just kind of want to start with polar and like what is polar? Well, polar uses a totally different coordinate system. So not only is it a different way to write your equations and a different mode on the calculator, but it's a different grid system. Okay? It's not like square grids on the like an XY axis. Now, some curves can be drawn much easier in polar. Okay? I'm going to show you an example of a very simple one right now. A circle. Okay? I'm going to draw it in y equals mx plus b first. Or not y equals mx plus b, but y equals. Show you kind of how complicated it is. Then we'll look at it in polar. Okay, so let's say we want to draw a circle of radius 3. First of all, is a circle a function? Yep. No. Fails the vertical line test. So technically, I can't draw a circle because I'm in function mode. But I can kind of cheat and draw a circle. So, what did I say? Radius 3? So let's do the square root of 9 minus x squared. That's the equation of a circle, except I got y by itself. Okay, that's the way I typed it in. So to get y by itself, you'd have to move x squared to the other side and then take the square root. Now, if that's all you draw, watch what happens. Is that a circle?
No.
No, it's only half a circle. So to get the other half, we have to do the negative, because when you take a square root, there's always two answers, the positive and the negative. And now, but that's the best I can do, and it doesn't even really connect nicely. But that's a circle with a radius of 3. So that's one way to do it. So that's function mode on the calculator, and the equations I had to do were the square root of, is it x squared minus 9? 9 minus x squared. 9 minus x squared, and the negative square root of 9 minus x squared. I mean, not a ton of stuff, but definitely a good amount of stuff you had to type in. Right. Now, let's go to parametric. So parametric is what we did yesterday. To draw a circle there, a little bit, I mean, it's different. It doesn't use squaring and square rooting, but it does use trig functions. So we have to type in 3 cosine t and 3 sine t. And there's your circle of radius 3, and doing it parametrically. Right, so that's parametric. And the two equations were, let's go back here, we had an x1 and a y1. x1, y1. So we're not putting two equations because we're drawing the top half and the bottom half separate. We're using two equations parametrically because one is for the x values, one is for the y values. All right, so that was 3 cosine t, 3 sine t. Okay. And now the last one is polar. So if we go to polar, put it in polar. Now when I go to y equals, the screen looks different again. It says r equals. If I put in 3, I'm done. So very, very simple to draw a circle in polar. So there's polar. So polar. Now, does that mean polar is always the best for everything? No, polar is not that good for lines. If you really want to draw a line, function is the way to go. Y equals mx plus b is definitely the simplest. Tomorrow I will show you the equation of a line in polar. It's a lot more complicated than y equals mx plus b. Just like the equation of a circle here is a lot more complicated than it would be in polar. So we use whatever graphing system makes it the easiest for us to graph what we're trying to graph. But you can pretty much graph anything in any coordinate system, really. Right? Whether or not it's going to be a mess, well, it depends what you're trying to graph. So any questions on that? All right. So polar, okay, the way a polar coordinate system works, and you can't really do it on a graphing calculator. The calculator won't display these circles. Even if you turn on the grid lines in the background, it just puts rectangular. Oh, actually, wait a minute. What if I do polar and I hit graph? That didn't do much. Let me put grid lines on and see if that actually does something. I really just put them rectangular. I don't know if you can actually put them in circular. That's okay, doesn't really matter. All right, so what we used to call the origin when you have a polar graphing system, it's called the pole. And you can still call it the origin, but it's really the pole. And when you graph a point in polar, it doesn't use x and y. Okay? Parametric uses x and y. Function uses x and y. Polar uses something different. A point in polar is r comma theta. Now, polar, we're kind of dealing with these like concentric circles. So what do you think r would stand for when we're dealing with the circles? Yeah? Radius. So basically, r tells you a distance from the pole. We're going to write it down, but r can be positive or negative. If r is positive, you move out the number of rings to the right. If r is negative, you move out that number of rings to the left. And you can go in between too. So like if I said r is 3.5, 1, 2, 3.5, you'd start right there. Okay, but that's not the final answer. Okay, just like x and y, you've got to do both parts of the coordinate. So you move out the number of rings indicated by r, and then theta. What does theta usually represent? Yeah, it's an angle. So then, like let's say you move out 3.5 rings, then from that spot, I will tell you to move a certain amount of degrees, or radians. Now, an angle can be positive or negative. The angle, think of angular movement. When you move on a circle, we don't describe it as up, down, left, and right. What are the two directions you can move circularly? Yeah?
Clockwise and counterclockwise.
Right. So depending on if the angle is positive or negative, you're either going to go clockwise or counterclockwise. Right? So the way this grid is set up, I think each line is 15 degrees. So that's 0, 15, 30, 45, 60, 75, 90. Right? You can get polar graph paper with more or less divisions. This also has a lot of small circles. So you could graph a radius up to 6, 7, 8, 9, 10, 11, up to 12 on this one. Okay. Sometimes I might use a larger polar graph, like this one. Okay. A little bit more spread out on R, so it makes it a little bigger. That's the smallest one I have. That's kind of hard to see, but on paper, if you had a big radius, you might want to use that. All right. I usually use one kind of in the middle. All right. So how do you graph the point r theta? Kind of told you as we were going through it. If r is positive, you're going to move to the right. R units. If r is negative, you're going to move to the left. So r is kind of like an x value. Kind of the same idea. So wherever you move, whether it's right or left, that becomes your 0 point. All right. So like, let's say, I'm just going to go back for a second. Let's say R was, I don't know, 5. 1, 2, 3, 4, 5. So you're starting from there. And now if I said to move 45 degrees clockwise, it's from where the X is. So 45 degrees clockwise in this case would be 15, 30, 45 degrees clockwise. That's where you would end up. Now, same thing. I'm going to move 45 degrees clockwise, but let's say R was -5. You'd start there. That is your 0. So when you move 45 degrees clockwise, now, starting from here, 15, 30, you end up there. All right, so that's the important thing. When you move the number of degrees, it's always from where you ended up after you did R. So now, if it's greater than 0, you're going to go clockwise. If it's less than 0, greater than 0, counterclockwise, less than 0, clockwise. And again, that's what I just emphasized. And so we're going to practice graphing some points in polar. We'll look at all the different combinations you could have, like positive radius, positive angle, positive radius, negative angle, all the different things. And then I think towards the end of class and in part tomorrow, we're going to look at how you could change something from polar back to XY coordinates. Okay, so we're going to learn how to convert between polar and what we call rectangular, which is XY.
Wait, if it's less than, you move clockwise?
If it's less than, you move clockwise. Yep. So if you have a negative angle, that's when you move clockwise. Okay. Any other questions on those two steps? So for the homework, you're going to need, well, polar graph paper for some of it. So I don't have any copy, but I can copy some if you want to pick some up after lunch. Or if you just draw a polar grid one time, then all you have to do is just label each problem. You know? Like just say, oh, that's number 2, number 6, number 7. Then you can really use the same grid for every problem, so you don't have to draw it once. Okay? Or if you want polar graph paper, just let me know, and I'll just photocopy it. Or I can print some out. All right. So we're going to start with the point 3, 45 degrees. All right. So first one we're going to look at is 3, 45 degrees. Kaya, what's my radius in that one? 3. So let's label that radius. And Natalie, what's my angle?
45 degrees.
45 degrees. So you're going to start by going 3 units from the pole. Gabe, do I go 3 units right or 3 units left?
Right.
Yep, 3 units to the right. I'm just going to put a temporary X there. I'm actually going to erase that in a second. And now I don't have the lines, but I'm going to go 45 degrees which way? Clockwise or counterclockwise? Yep, counterclockwise. So you should be right about there. And that's how you graph the point 3, 45 degrees. Okay, so on yours, what I would probably do is I wouldn't do each example on its own thing. I would just label this one and put example 1 next to it, and then you could probably put example 2 on the same grid, since you only have 6 of them. But it's up to you. Okay, let's look at this one. Negative 275 degrees. All right, so Chris, what do I do? I know I'm going to move 2 units away from the pole. Which way do I move to start?
Left.
Left. So I'm going to start 2 units left. And now, Kathleen, I'm going to move 75 degrees which way?
Counterclockwise.
Counter clockwise. Yes, counterclockwise. So I don't have lines. So how much is 75 degrees in terms of a quadrant? Like, am I going to end up, am I still going to be in the quadrant? Am I going to go a little outside it? Like, how far should I move? I'm still going to be inside it. I'm 15 degrees short of the y-axis. So I would end up about right there. Anywhere in that area is fine. On yours, you can do it pretty much exact because you've got the grid line. The grid lines on your graph paper, it's the same as the ones I had earlier there. I think they're 15s. Okay, so let's look at this one. 3, -60. Kaylee, what am I going to do first to graph 3, -60?
You're going to move to the right 3.
To the right 3. All right. And now -60. How am I going to do -60? Yeah.
Move 60 degrees clockwise.
60 degrees clockwise. So 60, a little bit over half. It's maybe about right there. Any questions on that one? Right, so we did a positive, negative. We did negative, positive, positive, positive. Let's look at a negative, negative. So this is a negative, negative, but what else is different? Chris?
It's in radians.
Yeah, it's in radians. If you can do it in radians, fine. If you don't like the radians, then we'll just change to degrees. So let's change it. What's negative 3 pi over 2 in degrees? Yeah.
Never mind. First.
Yeah. Can you say it again? You're close.
Oh, negative.
Negative 270. Because pi over 2 is 90, and this is 90 tripled, and then a negative in front. So negative 270. All right, so -4, -270. How about Madison? How would I do this one?
You would move to the left 4.
Okay, so left 4. So I'm going to start here. Okay.
And then you would go clockwise 270.
I'm going to go clockwise 270 degrees. So that's 90, 180, 270. Now, for this one, I'm actually going to draw how I got there. I went left, and then I went clockwise, 270. What is another way that I could get to that same spot besides a -4, -270? Rob?
Negative 490.
All right, so we could do -4, 90. Okay, and I'm going to draw that one. So -4 brings me left 4, and then 90 degrees counterclockwise. That's like that. Okay. What's another way I could get to that point besides -4, -90? Yeah.
490.
Sorry, yeah, go ahead.
The same thing anyways.
He said the same thing. What did you guys both say?
4 negative 90.
4, -90. So that's right 4. It's the first one we've had that goes right, and then -90. Brings me down there. And there's one more way. We've got a negative, negative. We've got a negative, positive. We've got a positive, negative. We're missing positive, positive. That would be the last way. Yep.
4 270.
4, 270. So right 4, and then 270 counterclockwise. So what I'm trying to show you there is when you want to graph or you're given a point in polar and they ask how do you get here, there's always 4 ways. You can have a positive or negative radius and a positive or negative angle. Now, if you said, well, what about something like, let's take and add 360 to that. 4, 630. Well, yes, that will get you to that point too by basically going like this. 4 going around twice and then stopping. That's not really a different way, right? If we were going to count all those as different ways, then there would be an infinite number of ways. Right. That one would still be considered positive. Right? So there's 4 basic ways to get to every point. And the reason I show you that is because if you get an answer on a test, like you do out a calculation, maybe you converted a rectangular point to polar, and you got this answer when you did it. But if it was a multiple choice, maybe that answer would be the one listed. You just have to know that what's in blue and red are the same. Okay? I think that you could come up with formulas like, oh, if you've got the negative, just add 360 and that'll give you the positive. Or you could probably figure out shortcuts for all of them. But for me, I always find it easier to just look like visually, and then I can just see which way to go. But there are formulas you could come up with. But any questions on all those? All right, let's look at this one. 0, pi. What's my radius this time, Rob?
You just put the origin or the pole.
Well, let's just start with what's my radius?
0.
0, and what's my angle?
Pi.
Pi, which is the same as 180. So where did you think it would be?
Would it just be at the pole origin?
At the pole, but then it's
You would go
an angle of what?
180.
180.
So would it just be a line and then a line?
No, we're just graphing points. So it's just a point. So it's a point at the pole, like that. But see how the green handle's at the top? You have to rotate it 180, just like that. Any question on that? So the way I'm going to look for that on the test, I'm just going to look for the spin. So you just put your pencil down, and you just give it half a spin.
1/2 spin.
Yeah, half spin. There you go. I did that pretty straight. All right, so 0, anything. It's always just at the origin. It doesn't move. It's just like it spins in place. You can't even tell. Now,
Is that just a late April Fool's joke?
how about what?
Is that a late April Fool's Day joke? Like, are you being serious?
It's just me being me.
Okay.
Sure, we're near April Fool's, so why not? So 2.5, 0 degrees. Is this one going to be at the origin?
No.
No. This time the angle does make a difference, because if it wasn't 0 degrees, it would move. But it is 0. So where does this one end up? Yep.
It's going to end up being positive x-axis.
Yep. Positive x-axis, how many units away from the origin? 2.5. So right there. And there are 4 other ways you could get to that point besides that one. You could do -2.5, 180, -2.5, -180, and actually that would be it. So there are not 4 different ways to get to that point. There's only 2. There's only 3. And that's because it's on an axis. Any questions on that one? Great. So we looked at all the different cases: positives, negatives, and zeros. That's just another positive. Okay. So we already kind of pointed that out, that there is more than one way to get to a point in polar. Is that true in rectangular with xy coordinates? No. Like if I had this, and I want to get to that point, there is only one coordinate that gets you to that spot, 2, 1. It's not like you say, well, it could be 2, 1, or it could be 1, -2. No. 2, 1 is the only way to get there. So that's a big difference between polar and rectangular. Given the choice of which way you could write it in polar, which way do you think we would prefer? Like the big positive? Yeah, positive. Okay, so let's look at how we can change from polar to rectangular. Remind me, what two letters does polar use? Yeah.
R and theta.
Uses R and theta. And what two letters does a rectangular grid use? X and Y. So the goal, whether you're converting a polar point or a polar equation, which we haven't done yet, you have to replace the R's and the thetas with X's and Y's. So I'm going to draw a diagram to do this. And what do you think is going to be part of the diagram? We usually do this kind of stuff. Yep.
Circle?
Yep, I'm going to have a circle. What else am I going to have in the diagram? I'm going to have a point that just represents a spot in the circle somewhere. But something else very important in the circle. Yeah? A triangle. Yep, I'm going to have some kind of triangle in the circle. When in doubt, you're in trig, the answer is a triangle. So, there's our circle. Let's put a point. It doesn't really matter where you put it, but just put it anywhere on the circle. And let's pretend that that's a point in polar. So I would know two things about it. I would know that distance. Okay, that would be the radius. Okay, so I would be given that piece of information, and I would also be given the angle. Where would the angle be in that picture? Where would I label it? You could say like between something and something. Yeah.
Between the 90 the flat line and the R, that little curve from the triangle.
So right in here?
Yeah. That other curve.
Not up there. Yeah.
Between the R and the X.
Yeah, between the R and the x-axis. So down there. Now, we want to somehow get rid of that R and the theta, so we're going to make a triangle out of that. How could I make a triangle out of what I have? I pretty much have what I need. I just got to add one more thing. Yep.
You could draw a straight line from the dot to the x-axis and make it a right angle.
Okay, because I was going to go like that. So yes, draw a line from the point to the x-axis, make it a right angle. There's no way around that, so I can only draw it this way. Let's put it. Right there. That's close enough. All right, so there's our right angle. All right, now the bottom side of that triangle from, let's go like this, from here to here is the horizontal distance that you have to move from the origin to start to get over towards that point. What do we normally call that distance? Yeah? That's the x. If you're writing a coordinate, that's the x value. Then from there, you have to go up that vertical distance. What do we normally call the vertical distance? The y. So our goal is to figure out x and y in terms of r and theta. And this is going to kind of look like something we did yesterday. It's kind of very similar. So let's start with x. You're going to know r, you're going to know theta, and you want to find x. How could you find how long the bottom side of that triangle is? As long as you know r and theta. Cosine, yeah. So the cosine of theta equals, what would be the fraction on the other side? X over r. Now, just get x by itself, and that's the formula for x. So what would x equal? Yeah, very good. R cosine theta. So if they give you an r and a theta as a point, and you want to know what would that be if I change it to an x value, do the r times the cosine of the theta. How about my formula for y? It would be r sine theta. R sine theta. And that kind of looks like a parametric equation. It's not parametric, right? Because we're not thinking of it that way right now, but it's basically what we did when we found the equation of the circle. Okay, so any questions on those two formulas? So let's try an example. So let's convert 2 negative 200 to rectangular. Okay, so two things I need. I need the x, I need the y. Ashley, what is the formula that I'm going to write down to find x?
R cosine.
Okay. And can you fill in these values for me?
2 cosine. 200 degrees. Or negative 200.
It actually wouldn't matter because remember when we talked about even odd identities, if you take the negative away from a cosine, the negative doesn't even make a difference on cosine. But we should just leave it there, just so we don't mess anything up. So 2 cosine negative 200. And how about my formula for y? Chris?
2 sine negative 200.
2 sine negative 200, which technically is the same as the negative. Put the negative in front, like negative 2 sine 200, right? But we'll just type it in and see what we get. All right, what should I do first to type this in?
Put in degrees.
Yeah, put it in degrees. I mean, you might get a problem in radians, but this one is not. So put it in degrees. 2 cosine negative 200 and 2 sine negative 200. Okay, so the x value is negative, let's just put it over here, negative 1.88, comma, and the y value is 0.68. Okay, so a lot of times a coordinate that looked nice in polar, two pretty nice numbers, when you change to rectangular, it's not so nice of a number. It depends on the problem. But any questions on that? All right, so now I'm going to take the point that I have, 2 negative 200, and what I did is I graphed it on the circle on the right. So I went 2 to the right, and then I went negative 200 degrees. So that's 200 degrees clockwise. So that would be halfway around. That would be 180. If I went to the first line, that would be 195. So I'm just a little bit after the first line. So any questions, or does anybody think I graphed that point wrong? Okay, so now what I'm going to do is I'm going to make this full screen. I'm going to take a rectangular grid that has the same scale, right? So basically, it's going to have vertical lines like here, 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 and the horizontals would be spaced exactly the same. So it's the same size scale. I'm going to take the rectangular and drop it in. The point's going to stay right where it is. So as long as I use the same scale, it should look like this point is almost 2 units left and a little more than half a unit up. So let's see if it works. So let's take this. So it should look like it's almost 2 units left and a little more than half a unit up. Is that how it looks?
Yeah.
Huh? Okay. So yeah, that's pretty good. So you can't really do that on paper, but I did it on the computer, so you can just kind of change the background behind it, leave the point right where it is. So we did it perfect. Is there any questions on that? All right, so that's that one. I got one more. This one's just in radians. No reason to change radians to degrees. I would just change the mode on the calculator. Right, so Joe, what's my formula going to be for x this time?
2, or the 3 cosine 5 pi over 6.
Yep. 3 cosine 5 pi over 6. And Renee, how about the formula for y?
3 sine 5 pi over 6.
5 pi over 6. Yep. Okay, so let's do this and see what we get. I'm going to do cosine 5 pi over 6 just by itself first. Okay, and let's see what we get. So cosine 5 pi over 6. That's a special number, 0.866. Does anybody remember what that is as a fraction? It involves something we did when we did unit circle trig. What kind of fractions came up a lot when we did unit circle trig? They involved what's that?
Root 3 over 2.
Yes, they involve square roots, and that one is close to the square root of 3 over 2, but this one is what kind of number? No, the 2 over 2 is the other one. That's 0.707 if we see that come on. But that's not root 3 over 2.
Negative.
Negative root 3 over 2. Negative square root of 3 over 2. So when you get an angle that's a multiple of 30 or 45, they're going to have you write the answer this way. Okay. Why didn't I do that here? Because that is not a multiple of 30 or 45. So you just round it off. Okay. That is 30 times 5. That's 150 degrees. Okay, so that is a multiple of 30. All right. So it's negative root 3 over 2 for the x. And we still have that 3 in front. The reason I didn't multiply the 3 out and just do it all in one step and get that is because if I saw negative 2.59, I wouldn't recognize it. It would have been something I should have recognized, but since you've tripled it, I wouldn't recognize it. But I did recognize it before I tripled it. So now I'll triple it. There you go. So it's negative 3 root 3 over 2. Now, when you're dealing with an angle that's a multiple of 30, if one of them comes out kind of messy with the square root, usually the other one doesn't. So let's do the sine of 5 pi over 6. 5 pi over 6. So that one is a half. So we have 3 times a half, which is 3 halves. Or you could do 1.5. Okay, so the only special fractions you need to know are root 3 over 2, that's when you get 0.866, and root 2 over 2 is when you get 0.707. Since all you're doing is sine and cosine, those are the only two you would ever see. If we had tangent involved, there would be others, but you don't. Okay, so we get negative 3 root 3 over 2, comma, 3 over 2. So you'd probably see an answer like that on the test being exact. If you got a decimal, well, you could always take this and actually do it out and get the decimal and see if it matches what you got. That's probably how I would write it. Any questions on that? So that's changing from, which way did we just go? From polar to rectangular. Okay, let's finish up by changing it back the other way. All right, so go through it one more time. In rectangular, which two letters do they always give you?
X and Y.
They're going to give you an X and a Y. But if you're trying to get it into polar, what letters do you want?
R.
You need to find a radius and an angle. I'm going to draw a diagram again. What do you think is going to be in my diagram? Circle? Yep. What else? Triangle. It's going to look like the same diagram. Pretty much. But this time, I'm going to circle what you know. Last time it was the r and the theta. This time it's the x and the y. You have to find r and theta. How would you get r? What is it? Yeah, Pythagorean Theorem. I'm going to write this down nicely on the next page because I just want, I'll write it nice so you can just watch for now. But yes, to find r, you would use Pythagorean Theorem. Now, what trig function would involve x and y? From the perspective of theta, yeah? Tangent. So if I set that up, and again, I'm going to put this nice on the next page. Tangent would equal what over what? Opposite over adjacent. Y over x. That's not theta though. That gives me tan theta. How would I get theta?
You take the inverse tangent.
Yep, I would take the inverse tangent. So theta is the inverse tangent of y over x. Alright. So to convert from rectangular to polar, I'm going to write down what we just said, but you have to do this first. You have to know what quadrant your point is in. You're going to see why that's important in a second. Once you know what quadrant your point is in that you're trying to convert, then you can find the angle. If your point is in quadrants 1 or 4, it's exactly what we just said. It's the inverse tangent of y over x. But if you do inverse tangent on your calculator and you hit enter, you're always going to get an answer between two things. Does anybody remember what inverse tangent always gives you a number between? It's negative this and positive this. It's not negative 1 and 1. Yeah? It doesn't go that high. No, it's much lower. Negative blank and positive blank. Not even that high. 90. It'll always be between 90 and negative 90. That's the definition of inverse tangent. It's always between negative 90 and 90. Well, that's kind of a problem because negative 90 is this way. So if you get an answer down here, you're covered. Positive 90 is this way. So if you get an answer up there, you're covered. So 1 and 4 work fine. But which quadrants are left out? 2 and 3. Inverse tangent will never give you an answer in quadrants 2 and 3. But you definitely could have a coordinate in 2 and 3, like that one right there. So how would you do it? Well, you have to make a small adjustment to the formula. You still have to do the inverse tangent of y over x, but in the front of it, you have to do plus pi, okay, if you're in radians, or plus 180 if you're in degrees. So by adding 180, what that basically does is it kind of shifts you over to the other half of that circle. So now you can get an answer in quadrants 2 or 3. But that still doesn't cover everything. This covers quadrants 1, 2, 3, and 4. Where else could you be?
On the x and y axis.
You could be on an axis. And the problem if you're on an axis is, let's look at this point. What's the x value of that point? 0. We don't know the y value, it just doesn't matter. It's 0 comma something. What would happen if you tried to plug in that point into the formula for inverse tangent?
Undefined.
Yeah, you'd end up dividing by 0. And we know that that's 90 degrees. So there it is an answer, but this formula doesn't give it to you. So these formulas work if you're in the quadrants. If you're on an axis, you just have to memorize it's one of those 4 answers. 0, 90, 180, 270. So that's how you find your angle. either the inverse tangent of y over x or 180 plus inverse tangent y over x. Other than that, it should be one you can just look at and get an answer. Okay. And then to find r, it's just the Pythagorean theorem. I'm just using the letters x and y because that's usually what you use for a coordinate. So r squared equals x squared plus y squared. This doesn't matter the quadrant. Pythagorean theorem is always the same, no matter what quadrant you're in. Okay, so let's finish up by trying an example from polar to rectangular.
From rectangular to polar.
Yeah, I'm sorry, rectangular to polar. We already did the other one. So convert to polar. All right, first kind of problem, this is the more typical, normal kind of problem. It's not on an axis, there's nothing quick really. The second one is very fast because it's on an axis. All right, so let's start with this. What quadrant is that point in? Let's see, write 3 down 5. Yep, you don't even really have to graph it. If you can figure out the quadrant in your head, that's fine. So we know it's in quadrant 4. So when I find the angle, do I add 180 or no? No. It's just the inverse tangent. What goes on the top? What goes on the bottom? -5 on the top, 3 on the bottom. Okay, so let's see what we get. I'm gonna do it in degrees. So second inverse tangent, -5/3. So I'm expecting this angle to probably be, I don't know, maybe -60, somewhere around there. -59. So about -59.04. Okay, so there's my angle. And what's the other thing I need? What letter? R. And how do we get R? Just do the Pythagorean theorem. R squared equals, what's x squared? 9. And -5 squared. So R is the square root of 34. If you can reduce it, as always, make sure you reduce that square root. Okay. So the answer in polar is going to be R, comma, theta. Now, it's kind of a little weird to write an answer like that because it's like you used an exact number here and then a rounded number here. Usually, with that kind of problem, we would probably just round everything. So you'd probably see it as like 5.83. So it takes a little bit of time because you got to do the inverse tangent and the Pythagorean theorem. Here you don't. 0.6. Where's the point 0.6? Yeah, it's just up 6. So as long as you know that it's up, you already know your angle is 90. Now, you don't really need to do Pythagorean theorem to figure out the distance from here to here. How far is that point from the origin? 6. I mean, you can do Pythagorean theorem. 0 squared plus 6 squared equals r squared, but you're just going to get 6. And now, how many different ways could this point be written on the test?
4.
Could be 4 different ways. But we did that earlier. Okay. So any questions on that? So tomorrow we'll get into actual polar graphing and then converting between like polar and parametric. Okay, so we'll make the connection between the past 2 days. Okay, so homework tonight, 1 through 16. Just all. And then I would just use your graph paper. You probably have enough, hopefully left over. You can just use that.